Learn like a pro.
Welcome! Today, we're diving into the geometry of how we actually see the world. We're going to build a complete model of reflection right from the ground up, using the clean, predictable rules of light to figure out exactly what's happening when you look in a mirror.
So, here's our game plan. We're going to start with the absolute basics of light, then establish the laws that control reflection. See how those laws explain why some surfaces are shiny and others aren't, demystify the image in the mirror, and then finally put it all together to build a perfect ray diagram ourselves.
Okay, first things first, we need to lay down the foundational rules. You can think of these as the non-negotiable axioms of light, that absolutely everything else is built on.
There are just three things you need to lock in. 1. Light travels in perfectly straight lines. No swerving, no curving. 2. It's a pure form of energy. And 3. In the total emptiness of a vacuum, it clocks in at 300 million meters per second. That's the ultimate speed limit in the universe. These are our ground truths.
All right, now that we have those fundamentals established, we can define exactly what happens when that light actually hits something. These are the laws of reflection.
So, to talk about this properly, we all need to be using the same terms. The ray of light heading towards the mirror, that's the incident ray. The one bouncing off, that's the reflected ray. And the most important player on the field for us is the normal. It's an imaginary line we draw at a perfect 90-degree angle to the surface, right at the point of impact.
You know, all of reflection, no matter how complex it seems, just boils down to two incredibly simple, unbreakable laws. First, the angle of incidence, that's the angle between the incoming ray and the normal, is always exactly equal to the angle of reflection. And second, all three of those lines, the incident ray, the reflected ray, and the normal, all lie on the exact same flat surface or plane.
And you can see that first law right here in action. It doesn't matter what the angle is. If light comes in at 40 degrees relative to the normal, it's going to leave at 40 degrees. If it's 60, it leaves at 60. It's this perfect, predictable geometric symmetry every single time.
Now, with these laws in our back pocket, we can finally answer a pretty basic question. Why does a mirror give you a clear image, but that wall right next to it doesn't? Well, it all comes down to the texture of the surface.
So, on a super smooth surface, like a mirror, a bunch of parallel light rays all come in and hit at the same angle. That means they all bounce off in parallel too, which keeps the image intact. But on a rough surface, the normals at each point are all facing in different directions. So even though every single ray still obeys the law of reflection perfectly, they all end up scattering in a million different directions. The light gets diffused.
Okay, so this leads us to something really fascinating, and honestly, a little bit weird. When you look into a mirror, you see yourself behind the glass. But how is that even possible?
I mean, really think about it. The mirror is a solid, opaque object. Light from you hits the front of it and bounces off. There's no way it can go through it. So how on earth can we see an image in a place where light from the object can't possibly be?
The answer is just a brilliant trick played by our own brains. See, your brain is hardwired with that very first rule we talked about. Light travels in straight lines. So, when these reflected rays hit your eye, your brain has no idea they've bounced off a surface. It just traces them backward in a straight line until they meet at a point that seems to be behind the mirror. This is what we call a virtual or phantom image. Now, this virtual image has 5 very specific, very predictable properties. It's virtual, it's upright, not upside down. It's laterally inverted, which is just a fancy way of saying left and right are flipped. It's the exact same size as the real object, and this is a big one. It appears to be the exact same distance behind the mirror as the object is in front of it. Let's just double-click on that word virtual for a second because it's the most important one. All it means is that there are no actual light rays meeting at the image's location. It's a phantom. It's an illusion created by your brain. That's why you can't hold up a piece of paper behind a mirror and see the image projected onto it, the way a movie projector creates a real image on a screen.
All right, enough theory. It's time to put all of this into practice. We're now going to combine everything we've just learned into a practical skill, building a geometrically perfect ray diagram from scratch.
We're going to follow a really strict 3-step method. The logic is to work backwards. We start in the virtual world that our brain sees, and then we connect it to the real world of physics. Step 1. We have to locate that virtual image, and we use one of our 5 rules to do it. Image distance equals object distance. So you just measure how far the object is from the mirror, and then you mark a point for the image at that exact same distance on the other side. Simple.
Step 2, now we draw the path that our brain thinks the light took. You draw perfectly straight lines from that virtual image point directly to the observer's eye. And you must use dotted lines here. That's the convention to show this is a virtual path. No actual light is traveling along it.
And finally, step 3. We draw the path the light actually took to make this happen. Draw solid lines from the real object to the exact points where your dotted lines hit the mirror. Those are your incident rays. Then, just connect those points on the mirror to the eye. Those are the reflected rays. And just like that, you've completed the real physical path of light.
And one last absolutely crucial check. Arrows. Your diagram isn't finished without them. This is a super common mistake, but the arrows are essential because they show the direction the light energy is actually flowing, from the object to the mirror and into the eye, so don't forget them. And there you have it, our finished product. You can literally see how all the rules we've talked about are working together in one diagram. The same distance rule placed the image. The dotted lines show the virtual path our brain creates, and the solid lines perfectly obey the law of reflection. This diagram, it's the geometric proof of what we perceive.
And this is way more than just a textbook exercise, you know? This precise geometric logic is the foundation for all of optics. The exact same rules we just used are what engineers use to design everything from the periscope on a submarine to the complex mirrors inside a telescope. The geometry of perception is absolutely everywhere.